Alright, so another quick video here about, this time from our section about estimating population variance and standard deviation, we had to find these chi-squared critical values. So I wanted to show you physically how to look those up on the table, since in the notes you couldn't really see where we're looking. And so we'll go down to the bottom of our formula tables here, right before the binomial distribution tables. It's a table A4 about the chi-squared distribution here. So just a couple examples. The first one that we were looking at, let's see, 95% confidence with n equals 25. So again, our degrees of freedom, just like for the t-distribution, is n minus 1. So 24 degrees of freedom. So if we're looking up a column, then we'd want to look up, looking up a row, then we want to look up the row corresponding to 24 degrees of freedom down that first column. And then we need to decide how much area is to the right of that critical value. Again, on this chi-squared distribution table, if you're used to area to the left from like the normal distribution tables and using those in the calculator as well, this one uses area to the right instead of area to the left. I honestly wish it did area to the left as well, but almost all the tables look like that. So we'll look at, let's see, 95% in the middle. Again, always helps to draw a picture on these when you're finding these critical values. So we'd have 0.05 left over, and dividing that up into each tail, we'd have 0.025, alpha over 2, in each tail. Okay? So to the right of our right critical value, to the right of our right tail, we have an area of 0.025. Alright, so on the right side of that chi-squared table, we see 0.025, and we'd want to read that down to 24 degrees of freedom. That's this gray row down here almost to the bottom. Okay, so 0.025, and read it down, we get 39.364 as our critical value. Okay. Now on the other side, on the left side of our distribution, we'd have chi-squared L with an area of how much to the right of it. Okay, 0.025 to the left, so the complement of that, 1 minus 0.025, would be 0.975, or just add up the areas to the right of it. 0.95 plus 0.025 gives us 0.975. Now you'll notice that this table is symmetric. The distribution isn't symmetric, but the table's symmetric. So on the third from the right column was 0.025. Now the third from the left column is 0.975. So you can kind of keep in mind that way. If you drew a line straight down the middle, then these areas to the right are symmetric on the left and right side of that table. So reading that column, 0.975 area to the right down to 24 degrees of freedom, we find 12.401. Okay. We tried another one with 99% confidence with n equals 41, so 40 degrees of freedom would be n minus 1. 99% in the middle would have 0.005 in each tail, so 0.005 to the right, over here on the far right column, and then in the far left column then would be 0.995. That would be our left critical value. And if we follow those down to 40 degrees of freedom, we find 20.707 as our left critical value and 66.766 as our right critical value there. Okay, so keep in mind, cut that area in half, the area that's left over in the two tails in half. Your area to the right would be half of that area that's left over, and then the complement of it is your area to the right of the left critical value. There's a bunch of area to the right. That's why we have these big numbers here from 0.9 and on up to the right of those critical values. Now if you're not in one of those values, then you're maybe a little bit stuck there, but these are the most common ones that show up, and that's why this table is kind of nice to use, because it works for all the common values. If you don't have a common value, if you're looking for like a, I don't know, 92% confidence interval, and your areas aren't on there, then you'd have to look it up somewhere else online, or using some other kind of computer software. Okay, we were also looking at calculating confidence intervals in this section for these types of problems. And to do that, sometimes we had to calculate a sample standard deviation. So I wanted to remind you of how to do that one more time. We've done this before way back in Chapter 3, but since it's maybe been a little while, I wanted to remind you of that. So under Stat, we'll go to Edit and enter our data in there. We were looking at these credit scores, and we needed the standard deviation as part of our finding the confidence interval for population standard deviation of those credit scores. So 661, 595, 548, 730 into stat edit into the first list there, 790 and 678 were our 6 credit scores. Okay, and we'll go to stat, calc, okay, over to calc, the middle menu up there, and 1-bar stats, and just hit enter twice on that. It gives us all kind of information. In particular, it gives us the sample standard deviation of 87.86 that we used in that problem. Gives us the mean, gives us the mean and all of that other information as well. Standard deviation in particular, that was what we were looking for on that one. We could follow that down and find median and our 5-number summary and all of that too if we needed to. Keep in mind for this section about finding confidence intervals for variance and standard deviation, we had to use the formulas by hand. You can use the calculator to help us find something like standard deviation and things like that, but there's no calculator command to help us out here. Under stat test, there's no chi-squared interval that we can use. You see there is a chi-squared test down there, but that does something different even than what we'll be doing when we do hypothesis testing later on. That does a little bit different type of chi-squared test called the goodness of fit test that we don't quite discuss in this course at least, but that's a more advanced statistics topic. So we don't have a chi-squared interval in here that we can use, so we have to do those by hand, but we have some things to help us out, like calculating that standard deviation using the calculator if we need to.